I wanted to start off by looking at the formation of a covalent bond a little bit more, which is what we talked about last time, specifically looking at that energy graph again. So I really like the way this shows how that energy changes when the bond is formed. So what you see here is two atoms that are very far apart, and what they're graphing is the energy. So if you look at this gray dot, that's where the energy currently is. Now I'm going to take the atoms and move them closer together. Remember, distance is on your x-axis. So currently these atoms are very far apart, so our distance would be great. But as we take this one and move it closer, energy is staying about the same for now. Notice that it starts to dip a little, little more. Notice those electrons. They're spinning around the individual atoms. Now they're starting to spend more time between them. Oop, I'm trying to keep them apart, but they're drawing closer together because of that attractive force. And that attractive force is causing them to dip. You see that? So if I let go, they'll stay right here, which is their perfect bond length. I'm going to try to get them closer together than that. Any closer than that, that energy is going up. And even as I try to drag my mouse, it's actually pushing them apart, because this is the bond length they want to be at, where the energy is the lowest. The attractive and the repulsive forces are balancing here. But if I try to push them any closer together, that potential energy is really going to skyrocket as those nuclei get too close together. So the bond length, as you see here where they're kind of settling back down, that bond length is going to be determined at that lowest point. And then if you move to the left onto the potential energy on the y-axis, you can find the bond energy from there. Alright, let's pick up where we left off on the notes, talking about resonance structures. So a resonance structure is a Lewis structure for an element, or for a compound, where you really need to draw multiple Lewis structures to show the full picture of what's happening in that compound. So in these molecules, you have double or triple bonds that could be located in different places. So that's the key for a resonance structure. You have to have double or triple bonds, and it has to be that it can be located between another set of atoms than where it is. So the result is two or more possible Lewis diagrams, and both of them are valid, equally valid. So if you think back to formal charge, both of these Lewis structures would have the exact same formal charge. They would both be equally as desirable for the compound. For example, if you draw the Lewis structure for ozone, you end up with the structure that you see on the left, with a double bond. But that double bond could just as easily be between the other oxygen atom. Okay, so that double bond that you see here on the left could just as easily be over on the right. And so that's what we show in the second Lewis structure. And in fact, the double bond is moving back and forth and back and forth. And so it's not in one place and it's not really in the other either. And so we wouldn't just draw one of them, or we couldn't and be correct. So we draw both of them, and we draw this double arrow to show us that the double bond is really not one place or the other, right? It's moving back and forth. And in reality, both of these bonds are the exact same, and they both contain 3 electrons. Okay, so that's kind of different, because we think, okay, over here there's a double bond, that's 4 electrons, and over here there's a single bond, that's 2. And then on the right-hand side, okay, now there's 4, and now there's 2 over here. But in fact, they kind of balance out, and so they each have 3 electrons in their bond. Okay, again, it's kind of odd, but that's what resonance is. Okay, it's actually this moving so fast of the double bond that it's like it's in both places at once, but neither at the same time. And so instead of saying there's 2 on this side, 4 on that side, if we were to say how many electrons there were, there'd actually be 3. Another way to say that is that there is 1.5 bonds between each of those oxygen atoms. And that's the way they're going to ask you on the AP exam. They would say, what is the bond order? You might be tempted to say 2 because you see a double bond, or 1 on the other side because there's a single bond. But a double bond moving back and forth is averaged, and so it's actually a 1.5 bond order, or 1.5 bonds. Alright, let's look at another example of nitrate. So if you look over here on the left, this might be the first Lewis structure that you draw for nitrate. Nitrogen needs a double bond in order to have 8 electrons. But that double bond could be there, could be at the top, which you see in the second Lewis structure, could be to the right, which you see in the third Lewis structure. So the location of that double bond is really here nor there. It's moving between all these, and we show that with these back and forth double arrows. So what would be the bond order here? Well, you have 4 total bonds, 1, 2, 3, 4, distributed among 3 atoms, those 3 oxygens. So really, that double bond is on each one a third of the time, right? It spends a third of the time here, a third of the time here, a third of the time here, 3 different locations. And they all keep their single bond all the time, so the bond order is 1.33, right? Single bond for sure, and then a double bond there a third of the time. Notice, just some reminders, this is a polyatomic ion, so we draw the Lewis structure in brackets and put the charge on the outside. Alright, one more example of a resonance structure in formate. So we have formate is CHO2, carbon in the middle, least electronegative. We have the hydrogen attached to the carbon, and then we have the 2 oxygens, and then we have a double bond so that carbon has an octet. That double bond could be 2, not 3 different places. So it could be here or here. Of course, it couldn't be on hydrogen. So we have this double bond moving back and forth, so it's on each oxygen half the time. So the bond order, or the number of bonds, is 1.5 between the carbon and oxygen. Now the carbon-hydrogen, that's just a single bond all the time. So its bond order would be 1. Okay, let's look at these two and answer this question. Which of these has the shortest bond? Well, they both have a double bond, and they both have some single bonds. They also both have resonance, so that double bond in the first one could go there, and in the second one it could go there, or it could go there. So let's think about the bond order. In this first one, that double bond has 2 places it can be, so it'll spend half the time at both. So their bond order will be 1.5. In the second example, though, that double bond has 3 places that it could be, so it will go to each of them a third of the time. So the bond order is 1.3, repeating. So which of these has a higher bond order? This one, right? The 1.5, where the double bond can only move 2 places. So the double bond is in each place more often than it is down here, so this one would have the shorter bonds. Okay, let's look at their explanation for this, and then you can go back again if you don't understand that. So in the first one, the number of bonds is effectively 1.5, because the double bond's on each one half the time. And then here, it is 1 1/3. So the one with the greater number of bonds, the 1.5, would have shorter bonds than the 1 1/3. Alright, to finish up here, we'll look at some limitations of a Lewis structure. So in some cases, the resonance must be used to show that the Lewis structure has multiple options. And the Lewis structure with resonance allows us to predict the number of bonds, the bond energy, and the bond length. So when we say that there's a limitation to the Lewis structure, what we're saying is that single Lewis structure, without showing the resonance, really doesn't tell us what's going on. We need to see the resonance in order to tell accurately how many bonds there are, what the bond energy is, and what the bond length would be.